Well, this is a slightly harder problem. It's at the end of the chapter on the Cayley-Hamilton theorem, and it is marked as a hard problem, and it's a little bit tricky. Various different ways of doing it. I hope what I'm going to show you is probably about the most straightforward way, I hope. Anyway, you've got a 2 by 2 matrix, and you're told that the cube of the matrix equals the square of the matrix, but the square doesn't equal A. And you want to show that in fact A squared is the zero matrix. One thing you do not want to do is to try and do it by algebra bashing, in the sense of putting A to be A, B, C, D and doing all that. That's not going to be a very sensible way to proceed here. We need something a little bit cleverer. The first thing when I come across problems like this, I worry about, does the matrix A have an inverse? So let's think about, does it have an inverse? Well, if A had an inverse, then I could take this equation and I could multiply both sides by the inverse, and I would end up with A squared equals A, but hang on, we were told that was not true. So that's the point about this in here. It's giving me the hint here, think about inverses. So A does not have an inverse. Otherwise, the equation A cubed equals A squared would imply that A squared equals A by simply multiplying both sides by the inverse. And that's false. So A does not have an inverse. That means the determinant of A must be 0. Now coming back to this whole chapter was on Cayley-Hamilton theorem. So I now want to turn my attention to what might the characteristic polynomial of this matrix look like. Well, let's have a look. The characteristic polynomial of this matrix A, what must it look like? Well, it's going to have to be lambda squared. It's going to have to be a quadratic because it's a mnemonic quadratic. Yep, I can make it a mnemonic quadratic. So lambda squared. Now it may have a lambda term, but if it had a constant term, remember that the constant term is the product of the eigenvalues, and one of them is 0 because the determinant is 0. And so that means the constant term here has to be 0. So the shape of the characteristic polynomial has to be lambda squared plus A lambda. We don't know what A is yet for some real number A. Yep. In fact, I might just rewrite this because I'm going to use Cayley-Hamilton. I might just put a minus in there just to make the algebra a little bit clearer. So I'm going to put a minus A. It doesn't matter if A or minus A. So by Cayley-Hamilton theorem, that tells me that A squared is equal to A times capital A. Okay, so we get to that point. Now again, go back and look at the data we're given. We're told that A squared was not A. So one thing's for sure, whatever A is, it ain't 1. It can't be 1. Righto, well, where do you go now? Well, we've got something about cubes in the original problem, so I might be tempted to multiply both sides by A. And so I get A cubed is A times A squared. And by the way, now this A cubed, remember, was A squared. So I can also say this is equal to A squared. I just simply replace the A cubed with the A squared. Well, hang on, this equation here looks very odd because it sort of looks like I've got a number times a matrix is that matrix. So that number has to be 1. But hang on, we were told up here it was not 1. So the only way that can happen, then is that this matrix A squared has to be the 0 matrix, since A was not 1. And that solves the problem.